Hello, Calculus 2, Math 1342. This is extra practice for quiz 4. Quiz 4 covers, this is sequences, introduction to series, and then just through Monday's class of 5-3. 5-3 is non-negative series and has so many tests, but this quiz just goes through Monday's class. So in particular, let's see, check Canvas because I will list the specific exercises from 5-3 that are relevant to this week's quiz. And then, well, the rest of 5-3 will be on next week's quiz. Okay, well, we begin with number 1, which is sequences. This is section 5.1. For each sequence, we want to determine whether or not it converges. And if it converges, write its limit in the blank. So on this, well, you notice we only have one thing in the numerator, is natural log. And then what dominates the denominator is this n. And the natural log, this part grows, maybe I should write a little bit of my work just because I am not just trying to work the problems, but trying to explain solutions. So the natural log grows significantly slower than n. And this means as a fraction, this will go to 0. So this converges to 0. Great. Bn. Well, in the numerator, we just have one term. It's here in factorial. And what dominates the denominator is this term. In factorial grows faster than n cubed. And so, well, it's the same, right? Factorial. So you see this also converges. But it converges to, we look at the coefficients. We have 1 in the numerator and a -5 in the denominator. This one converges to -1/5. Now for Cn. This sequence has a -1 to the n times something. And the way that I do these problems first, so this is for part C, we look at this. So 3 plus 1/n. Well, as n grows without bound, this approaches 3. And so what's happening to my actual sequence? Well, for n large, say here is 3, and here is -3. And for n large, my sequence is just doing like this, close to 3, right? It is bouncing back and forth, back and forth, back and forth, very, very close to 3 and -3. This would be what's happening to -1 to the n times 3 plus 1/n. So this one, you notice, diverges because it oscillates. Letter D. Well, cosine is a continuous function. 2 to the -n converges as n grows without bound. If you think about the corresponding continuous function of x, it looks like this. This is just 1/2 to the n, okay, on the inside. And this converges to 0. And so maybe I will write this as part of my justification. Not that it asked for it, but I'm trying to explain where my answers come from in this video. So here, the limit as n goes to infinity of dn, we may bring the limit inside the continuous function. And so we get the cosine of 0, and this is 1. So this sequence converges to 1. Number 2, we have 3 series here. And for each one, we want to determine whether the series converges or diverges and justify. Okay, we are not looking to find a sum here. We are just wanting to know whether or not each series converges. Okay, so what is the general strategy whenever you see a series? And this will remain true even as we move through more of 5-3 and 5-4 and learn more tests. Always first look at the terms and see if they go to 0. If they do not, you are finished. And this is going to be immediately an answer for A, because if you take a limit, say as n goes to infinity of the terms, which is the square root would be 8n divided by n plus 2. Well, this goes to the square root of 8, right? Because how would you see this? Here and here is the same power of n, and so we can look at the coefficients. We have 8 in the numerator and a 1n in the denominator. So inside the square root goes to 8, and then I really used the sort of bringing the limit inside a continuous function here. So this definitely converges to the square root of 8. But what's important for letter A is that this is not equal to 0. Now we quote the test by the term test, and then we state the conclusion, the series, and this one starts at 4, which is perfectly fine. We have a square root 8k divided by k plus 2. This diverges. Diverges is the only possible conclusion of the term test. You will never conclude converges using the term test. Never. It's just not a possible conclusion of that test. So be careful of this in your work. Well, we move on. Letter B. I can rewrite this in a way that makes it clear what the power is in the denominator. So you notice this is 1 over. We have n to the, well, it's a cube root of n squared. So my power is 2/3. Now, if we do the same strategy I mentioned in part A, we look at the terms and we ask ourselves, do they go to 0? The answer is yes, right? The terms go to 0. Term test gives us no conclusion here. But you notice this is a p-series. And p is 2/3, which is less than or equal to 1, and so diverges. And this is all we need here. This is the justification, right? The justification, when you have a p-series, you must state it's a p-series. What is p? And then if it's less than or equal to 1, you get diverges. If p is bigger than 1, you have converges. And really everything I wrote here needs to be included in your work. Okay, let's move on to part C. In letter C, well, same strategy every time I see a series. First, look at the terms. Here, my terms. Well, this is what dominates the numerator, and then I just have one term in the denominator. K to the 5th is a bigger power of k than k cubed, so the terms are going to 0. Term test tells us nothing. Okay, we have to move on. Think about something else. But here you notice I have a sum in my numerator. And so what I'm going to do is first look at this series. This is k equals 1 to infinity of 3 over k to the 5th. Okay. What do we see here? Well, this is a constant times a p-series where p is 5, strictly bigger than 1, converges. And then we can look at sort of the other term in the sum. It's here. Well, it would be k cubed over k to the 5th, which is a sum. K equals 1 to infinity of 1 over k squared. This is a p-series. And p equals 2, bigger than 1, converges. Now, my actual series is the sum of two convergent series. Let me write this. K equals 1 to infinity of 3 plus k cubed divided by k to the 5th. This is a sum of two convergent series, and this will converge. This was one of our properties of convergent series. And so letter 2C, this converges. It's a sum of two convergent p-series, in fact. Number 3, we will find the sum or show the series diverges, justify our response. There's a 3A, B, and C, and what we see on this page is A and B. We'll do these two first. Now, the first one, letter A, we just see the terms, and if you think how do we approach a series? First, you see, did the terms go to 0? And definitely you can tell the terms do, right? We have a fixed numerator in the terms, and then this denominator is getting bigger. The terms go to 0. Term test tells us nothing, okay? So we have to do something else. Term test will not apply. But you notice as we move from one to the next, what is going on? Well, we are multiplying by the exact same number every single time. I am multiplying by 1/5. So every time I move from one term to the next, I'm multiplying by 1/5. And this tells me I have a geometric series. What makes a geometric series geometric is exactly this. As you move from one term to the next, you are multiplying by the exact same number. Okay, so let's get started on letter A. This is geometric, definitely. My R is 1/5. Now, my initial term, this is not too hard to see. It's just right here. It's the very first term that you see. My initial term, A, is 2/25. Well, we note that absolute value of R is 1/5, which is less than 1. And so this geometric series converges. We are asked to find the sum though. And so this converges to A/1 minus R. And we can calculate this. This is 2/25 divided by 1 minus 1/5. Now, don't leave your answer like this, right? Do not leave your answer like this. We're going to leave this as, say, an integer or a simplified fraction. So we have 2/25 times, well, it's a 4/5 in the denominator. So I multiply by 5/4. Note that this is just 1/10. So we have 1/10. This is the sum of the series in letter A. Now let's move on to letter B. Well, it might not be so clear that this is geometric. We are looking at this in summation notation. And as I defined a geometric series, it went from 0 to infinity of A, R to the K, exactly like this. And if we look at this summation notation, we do not see it exactly like this, right? My index starts at 1, and then I just don't see it like this. But if you go back to thinking about what makes a geometric series geometric, or for instance, in part A, how did we figure out that was geometric? Well, we can figure this out by just writing out some terms and then realizing that sort of as you move one term to the next, we are multiplying by the exact same R. So let's do that here. For K equals 1, I have minus 3 squared over 4. This is K equals 1. And then K equals 2, I have minus 3 cubed over 4 squared. K equals 3, I have minus 3 to the 4th over 4 cubed. And you could keep writing if you wanted to. The next one would have minus 3 to the 5th over 4 to the 4th, etc. But you can see though, you see as we move from one term to the next, we are multiplying by minus 3 over 4. So definitely this is geometric. We see here is my R. So B is also geometric. My R is minus 3 over 4. And my initial term, well, I have it written down. It's just 9 over 4. But if you don't want to write out terms, let me move this down a little bit. If you don't want to write out terms like I did, all you would do is just take and evaluate this at your lowest index. In this case, my lowest index is 1. So I evaluate this expression at 1. This gives me my initial term. But you could also evaluate at 10 or 2 or 0 or whatever your lowest index is. This is how we find our initial term. Okay, great. Well, going back to this geometric series, we have A, we have R. Absolute value of R is 3 over 4, which is less than 1. And so this also converges and we are asked to find the sum. This converges to A over 1 minus R. Here, this is 9 over 4 divided by 1 plus 3/4. 1 minus negative 3/4 is 1 plus 3/4. Once again, we don't leave it like this. We want an integer or a simplified fraction. In the denominator, I have a 7 over 4. So I'm multiplying by 4 over 7. And here's the sum of my series. It's 9 over 7. So both of these are convergent geometric series, and we have found their sums in part A and part B. Letter C, same directions. We want to find the sum or show the series diverges. I'm going to ignore the hint for the moment, okay? What's my first strategy, right? Look at the terms. Do the terms go to 0? If I look at the terms, I will do this in highlighter, okay? Inside of the natural log is approaching 1, and so the terms themselves are going to the natural log of 1, which is 0. Okay, this means the term test tells us nothing. We cannot use term test here. Okay, so now let us try something else. And the something else comes from the hint. This is a telescoping series. Typically, when we have a telescoping series, we see a difference of 2 things as our kth term. And here I don't see that, but you note that I can write it that way. So that will be my first step. We may use log properties here. My kth term is ln k minus ln of k plus 1. Okay, and this is going to help me, now is when I can use the power of telescoping series. So how do we do this? Well, let's write out Sn. Sn, what does this mean? It means you add up to index n. So I just start writing out terms. First of all, k equals 2. We have ln 2 minus ln 3. And then k equals 3. We have ln 3 minus ln 4. And then k equals 4. We have ln 4 minus ln 5. Maybe I can write above, this was k equals 2, k equals 3, k equals 4. Okay, now I will just jump to k equals n. We have ln n minus ln of n plus 1. This would be k equals n. Okay, now here's where we realize we can get a closed formula for Sn, which is generally what's very hard with series. So these two add to 0. These two add to 0. This one with something here will add to 0, and then, well, the natural log, this one with something before, will add to 0. And so we have all of these in the middle, which are adding to 0. And we have Sn is just ln 2 minus ln of n plus 1. Well, definition of the sum of a series, or definition of whether or not a series converges. We take a limit as n goes to infinity of the partial sum Sn. If this limit is finite, then this is the sum of the series. And if this limit does not exist as a finite number, then the series diverges. This goes back to the definition of a convergent series. So we take a limit as n goes to infinity of ln 2 minus ln of n plus 1. Well, this part, natural log is growing without bound, right? And we have a minus in front. And so this is going to negative infinity. So this limit is minus infinity or does not exist as a finite number. And this means that the series k equals 2 to infinity of ln k over k plus 1, this series diverges. Okay, this was really using definition, but this diverges. We took a limit of the partial sums, and the limit did not exist as a finite number. This telescoping series diverges. Well, wonderful. This is the end of quiz 4 extra practice. Good luck on the quiz, and thank you very much.